This video is going to start talking about how to graph rational functions. So we are really still in Unit 6. We're just in the second half of the unit. In the first half of the unit, we were working with rational expressions and rational equations. And now we're going to look at, well, how do I graph those? So that's the first thing. The target up here really applies kind of to the whole chapter, the whole unit. But today we're going to specifically focus in on 1 over x and its transformations, and then we'll start getting into some of these other things, zeros, multiplicity, asymptotes. First of all, the first thing I want you to do is we are looking at the basic parent function, and I want you to take a minute to pause the video here and fill in the table. All right, your table should look like this. Remember, I've got an example here for -1/2. If you plug in a number into the denominator, then you basically multiply by that times the reciprocal, and so we would get this. So any way you get that table, you could use your TI-30, you could use your graphing calculator, you could use Desmos, or you can just kind of do it in your head. But one thing to pay attention to, and we talked about this a little bit a week or so ago, is that one of those numbers is undefined because you cannot have a 0 in the denominator. If you have a 0 in the denominator, that's undefined. And then we also discussed what does that mean if it's undefined as far as the graph goes. So right now, pause again and take a minute to plot these points onto the graph and see what you get. Okay, your graph should look something like this. And where it is undefined, usually we do want to draw that in. It is a dotted line, and it's at 0, at x equals 0. So in other words, it is a dotted line, yikes, right here. Sorry, mine's not very straight, but it's typically a dotted line, and what that does is it shows us the graph should not touch it. Now, my dotted line is kind of wide and not very well drawn, and so my red line is actually crossing it, but typically it does not cross that because it is undefined there, which means it does not exist there. That is the parent function, and I want us to just understand that this is what a parent function of the graph is going to look like. And then let's discuss some of the things that we have been talking about. It's undefined at x equals 0. What does that mean? It means it never touches the y-axis, just like I've drawn there. Now, here's something we haven't talked about. Where is it undefined for f of x? In other words, what can f of x never equal? And I'm going to say that y can never be 0. Let's look at the function again. So here's our function, and I'm saying that this function can never equal 0. Can you think of any number you could plug in for x where you would get 0? Like 1 over 1? No. 1 over 2? No. 1 over -1? No. 1 over half? No. 1 over 0? Undefined. There is no number that you could plug in for x that would ever get this equal to 0. So guess what? We have another asymptote. This time we have an asymptote here on the x-axis, and that's really bad. So that's what I'm saying. It has a couple different places where it's undefined. It never touches the y-axis because x cannot be 0, and it never touches the x-axis because y cannot be 0. So that's what this looks like. Now, an asymptote, we talked about that definition a little bit in class the other day. It is a line that the graph gets closer and closer to, but never reaches it. And I say within finite limits because really we say at infinity, it would get there. Well, we don't get to infinity, so we're not going to talk about that. You would talk about that in calculus. I also want to explain, I mentioned this the other day, that sometimes it can cross, the graph can cross the asymptote. So let me show you an example of that. And this is just going to be a really basic example. I don't know if you've ever seen a sine wave before, but sometimes there are graphs that have this pattern to them. And if these get smaller and smaller and smaller, and mine's not drawn perfectly, but if those get smaller and smaller and smaller, but they never land, they never end on that asymptote. So it's crossing a bunch of times, but it's only crossing so it can get closer and closer and closer and closer. Okay, so that's just to bring up with an asymptote. Sometimes the graph does touch it, but it doesn't stop there. It goes away and keeps getting closer and closer and closer. So that's why this definition says the line that the graph gets closer and closer to, but never reaches. All right, in this next section, I use this word conjecture. Hopefully that's a word you know from geometry. We make a lot of conjectures in geometry, I think. It's basically an educated guess. So can you make an educated guess about where the asymptotes would be for each of the functions below, and then check your conjectures with Desmos? Okay, before we do that, let's write out in the margin our HIVO rules, and I'm going to kind of clarify what HIVO means in this situation. In this situation, that is when we're dealing with rational expressions or rational functions, when we use HIVO, when I say inside, I'm talking about inside the fraction. It's like part of the fraction. When I say outside, I'm talking about outside of the fraction. So in other words, on this first example, where is it undefined? Wherever it's undefined, that would be my vertical asymptote. So where is it undefined as far as the denominator goes? Well, it's undefined at 3, right? And then the horizontal would be, what can f of x never equal? Well, again, I talked about that a second ago. If this is a 1, we can never get it down to 0. So our asymptotes in this case, our horizontal asymptote is at y equals 0, and our vertical asymptote is at x equals 3. Take a minute right now, pause the video, and see if you can make some conjectures, some guesses about the rest of these, and where would the asymptotes be. Okay, as far as the vertical asymptote, and again, let's write this down so that we don't forget, that the vertical asymptotes come from the denominator. So the vertical asymptotes come from the denominator. If I look at the denominator, x is equal to 3 is going to be an asymptote. That means it's undefined at 3. All of the rest of these, all they have, well, these next 3, all they have in the denominator is an x only, so that's going to be 0. On this one, if we set that 5x equal to 0, then x would just be 0 again. So what we're doing, we're finding these from this denominator, we're just setting the denominator equal to 0. That's what we're doing. And so x cannot be 0 in each of these cases. That means these are going to be vertical asymptotes. Let's also talk a little bit about the HIVO, the transformations. What's going on? Well, this 3 is inside the fraction. That means it's going right and left. And whenever it's inside, it's always opposite of how it seems. So this really means that this one is going right 3 units. So it's just like that function we had a minute ago, we're just moving it right 3. The next one, it's moving down 2. That's what that minus 2 means, is down 2. So that's why our vertical asymptote didn't change, we just moved it down. And so if we think about that, moving it down, then our horizontal asymptote is also moving down 2 units. The rest of the asymptotes here are just going to be zeros. Let's talk about transformations again. As far as transformations goes, this example, negative 1 over x, what is it going to do? It's going to reflect it. It's going to reflect it across the x-axis. This 5, what we've done is we've taken the parent function and we've multiplied it by 5. That means it's a vertical stretch by a factor of 5. This next one, we've multiplied it by 1/5. That still means it's vertical, except this time it's going to be a vertical shrink by a factor of 1/5. I'm going to take a second to show you these on Desmos so you can see what they look like. But one thing that we're going to pay attention to in just a minute is we're going to see that a vertical stretch and a vertical shrink doesn't really change the graph a whole lot. Okay, let's look at these graphs on Desmos. All right, on Desmos, I have the parent function here. This is what the parent function looks like. That's just the very basic. I'm going to go ahead and make that again, and this time I'm going to take it with. So here's our parent function. We discussed that this x minus 3, it should move it right 3 units. Let's see. Do you see how it's just moved right 3? I'm going to center my graph a little bit better. Okay, So that's just moved it right 3 units. There you go. This next one should take the parent function and should move it up 2. Oh, excuse me, down 2, right? We're going to move down 2. So here it is. We have moved down 2 units. You can see everything else is the same. The next one we said would be a reflection, so it should turn everything upside down. Here we go. Do you see how we took the whole thing and we flipped it over the x-axis? It's a reflection across the x-axis. This next one should be a vertical stretch. Now look at this. Can you see that vertical stretch? It stretched it. It basically just took it away from the origin. It's not as close to the origin as it was. So it is a vertical stretch, and it kind of took it farther from the axes as well. I'm going to zoom a little bit. I mean, look at that. It barely changed. The only places it changes it basically is maybe between 20 and -20. But when we're talking about functions, we want to be able to look a lot farther away than that. And past 20 and -20, it's not really much different. The only place it's different is here. So we really won't spend a whole lot of time talking about that because it's so similar. It is a transformation, but it just doesn't seem to make much sense to spend a whole lot of time talking about that kind of a transformation. Okay, let's take a look at the next one. Should be a shrink by a factor of 1/5. Now look at that again. Can you see it got closer, but really, I mean, it's just almost exactly the same. I'm going to put that 5/x. So here are the 3 different functions. The dotted line is the parent function. The line down here is 5/x, and the line up here is 1/5x. The 1/5x is a vertical shrink. So it shrunk it like from top to bottom. We pressed it from top to bottom, and when we did that, it got closer to the axis or closer to the origin. Okay, so those are the different transformations that you see on that table. I just wanted to give you a visual so you could see what they look like. Let's go back to the notes, and we're going to turn the page. Okay, similar deal here. We have another parent function. Now, I'm going to call this a parent function, which typically parent functions have to be completely unique from each other. And it looks really similar to what we just did, but it's an x squared. It's 1/x squared. And that is going to look different than the 1/x. And there's nothing you can really do to transform 1/x for it to look like this, so it is its own new parent function. Go ahead and plug those numbers in, however you want to do that, in your head, in your calculator, whatever. See what you get on your table when you plug those numbers in. All right, here's the table you should be getting. Notice all of my values are positive, because when you square something, it becomes positive. Whether it's negative going in or whether it's positive going in, we square it, it becomes positive. And once again, I'll focus just on one example. If we plug in a -1/2 and then we square it, well, 1 divided by that is like 1 times the reciprocal. And I square that, and -2 to the second power is a +4. So -1/2 should be +4. So all of these are positive values. Again, take a minute, pause the video, and graph this function. All right, look at what has happened. Since they are all positive, everything is above the x-axis. Before, I made a little dotted line to show you. This little dotted line is 1/x, but when we change it to 1/x squared, it jumps up here because it becomes positive, so everything's up above the x-axis. Here are our HIVO rules. The A, and I mentioned this a minute ago, the A doesn't change the graph much. It just makes it a little bit closer to the origin or farther away, depending on which way. But as far as a testing situation goes, I'm not going to test you on that because it's just really hard to see it or to graph it or anything. It's such a minute little change. So that A is not something we're really going to focus on as far as transformations go. The K, that's outside, and if it is outside, then that means it goes up and down. So you might take a minute to write that down, that is outside, whereas this box is the inside, and that is, remember, it's opposite of how we think it is going to be. It goes left when if h is less than 0. In other words, if it's a plus, it goes left. If it's a minus, it goes right. But we focused on that opposite thing a while. So this is just the basic transformations, our high-low rules for the parent function of 1 over x. And we're spending some time today going over 1 over x, but really what we're going to be graphing is going to be a lot more complex. But this is just a good starting point to look at and see how they work. Down here, we have a review. This is a review. This is observations of polynomial functions. That is our last unit from last semester. Do you remember how to do that? Do you remember where the zeros are? Okay, we have an x minus 2 and an x plus 3. What are our zeros going to be? Well, positive 2 and negative 3, because we set that equal to 0, we get 2. We set this equal to 0, we get negative 3. Multiplicity. Do you remember what multiplicity is? Multiplicity is the power that's on here, and if that is a 1, then there's no change. It just goes all the way through. If that is a 2, then there is a bounce on the axis, the x-axis. And if it is a power of 3, then there's a bend at the x-axis. So what's happening here is we have some zeros. I'm going to go ahead and plot those on there. We have an x equals 2, and x equals negative 3. It's going to go through at 2. It's going to bounce at negative 3. How do we draw that? Well, we have to look at the end behavior. And if you look at what's going on here, we have a negative sign, we have an x, and we have an x squared. And that comes out to be a negative x to the third. Do you remember what a negative x to the third end behavior looks like? It's going to look something like this. Now, one other thing that we might consider that's not listed here, but we might think about it, is what is the y-intercept? Well, remember, the y-intercept is where we plug in a 0 for x and then we work it out. So if we plugged in a 0 for x and we worked this out, I'm going to write this down. Then we're going to have a negative, plug in a 0, that's going to give me a negative 2, plug in a 0, that's going to give me a 3, but I also need to square it. So that is 9 times positive 2, that's a positive 18. So my y-intercept is at 0, 18. That's not going to fit on my graph, but I'm just going to kind of sketch it. Okay, so what's going to happen is I start at the top at positive infinity up here. I'm going to come down and go through, get a bounce at negative 3. So I'm going to come down, I'm going to bounce off negative 3, and I'm going to come all the way up here to positive 18. Well, that's not going to fit on my graph, but I'm going to go all the way up to positive 18. I'm going to come down here, and I'm going to go through 2, and then I'm done. That has the correct end behavior. It has approximately the right y-intercept. I just need to include my graph longer. It has a bounce and it has a through. That's what that would look like, basically. That's a review. We learned that last semester. Now let's talk about what's new. Well, what's new is, what if I throw a fraction in there? And what is that going to do to things? Well, as we look at this function, I think you know what the first thing is going to be to do, and that's going to be factor this. So let's go ahead and factor this, because now we're going to look at all of that information that we need about the graph. So what are the zeros? Well, the zeros come from the numerator. And so my zeros are positive 4 and negative 2. As far as multiplicity goes, again, that would be powers, so there is none. There's no multiplicity, we just go through on both of them. So I'm going to go ahead and plot those 2 points. The next thing is end behavior. I'm going to skip that for a second. I'm going to come back to it, because the next thing I want to look at is I want to look at vertical asymptotes. Vertical asymptotes come from the denominator. And so just like on the numerator, we set those equal to 0, in the denominator, we are also going to set this equal to 0. And we talked about that before. What is going to make it undefined? Well, things going to make it undefined is 1, positive 1. So I'm writing down here that the vertical asymptotes come from the denominator. It's where they make it undefined. I set it equal to 0 and I get 1. That is my vertical asymptote. So I need to draw my line at positive 1. It's just a dotted line at positive 1. It means that my function is never going to hit that line. Now, I might cross it. It's just never going to get there. Typically, it doesn't cross it, but there are situations where it might, but typically it does not cross it. Let's get back to end behavior for a minute. When we talk about end behavior, when we were in polynomials, when we talked about end behavior, it was just the x, like the power of how high would this power be, and we didn't really deal with the 2 and the 3. Same thing here. When we talk about end behavior, we're going to look at the powers, but we have to look at both powers, that is the numerator and the denominator. And as I look at that and I estimate that, that comes down to x squared over x. And x squared over x reduces down to positive x. Well, what does a positive x function look like? A positive x function has end behavior that looks like this. So this graph, and it's going to be tricky, but this graph is going to come down, start down here in the negative area. It's going to go through my negative 2, and it's going to not cross my asymptote. So it's going to look something like this. So this half of it looks something like this. The only place this is undefined is at 1. So I'm not going to put anything on that asymptote, but I do need stuff. I need a graph over here on the right, because look, I have a point for 1, but I also need a lot of points. I need another part of the function. Now, what defines, what tells us where to go next is the multiplicity on this denominator. And do you see it has a power of 1? That power of 1 means it has an odd multiplicity. Odd multiplicity means that you're going to go to opposite sides of infinity. What I mean by opposite sides of infinity, that you are here, and do you see how this is going all the way up to positive infinity? It's going to keep going and going and going. It's never going to hit the axis, but it's going to keep going up to positive infinity. The odd multiplicity says I need to go down to negative infinity. In other words, I need to come down here to negative infinity. So now I need to pick up my graph down here, not hitting the asymptote. And again, I'm going to go through, because there's no multiplicity on that. Sorry, bad line. And then I'm going to go over. This is what your graph is going to look like a little bit. Let me show you on Desmos what that looks like. I'm actually going to back up and show you, first of all, the graph that we did up above here. Mine is in blue. This one, I'm going to show you that on Desmos, and then I'll show you what we have down here. Okay, first of all, here is the graph from the polynomial. Remember that it had I'm going to zoom in here. It had an x-intercept at 18. So there's our 0, 18 x-intercept, y-intercept. Now its max is higher than that. The relative max was 18.519. We didn't really get there. We were just trying to estimate the graph. That's fine. Down here it has x-intercept at -3 and another one at 2. So that's the graph we basically drew. The end behavior was going from positive infinity all the way down to negative infinity. And then lastly, this graph looks like this, and it looks kind of funky. And I'm going to tell you, and we'll talk about it in just a second, that it has an asymptote at the line x minus 1. Let's go back to our paper. We are almost finished here for today. The asymptote, and some of the hours we talked about this the other day, I'm not sure if all of them did that, is we basically did long division or synthetic division with this. If I did synthetic division with this, I would have this. And if I do my synthetic division, then I'm going to have, do you see that this is x minus 1? And just a minute ago on Desmos I showed you x minus 1. So it's here at -1, goes up 1 over 1. So that is this is called a slant asymptote. But this is what it looks like. We will delve more into this. We're going to do pages 3 and 4 tomorrow, but I know this is a lot of weird looking stuff. It's new to you, so we're going to spend a lot of time graphing. We will get lots of practice with graphing, and please write down your questions. Bring your questions to class tomorrow.